The we'll look at another aspect, that is the state assignment for uh, for asynchronous circuits. So that is where we stopped last time. Before we start that, let us just confirm. So your exam will be on 15th April from 2:30 p.m. onwards. Okay. All right. So yeah, just a minute. Okay. So continuing from where I stopped last time, uh, continuing from where I stopped last time. So this was one machine which was synthesized, uh, and this is the result of different groupings of the merger graph, different groupings of state for the merger graph. Okay, so now let us just see. So these are the so this one is a state machine. Okay, so as you can see that S0 is stable for the input 0 1. So for 0 1, S0 is a stable state. S1 is stable for the input 1 0. Similarly, S3 is stable for the input 0 0 or 1 0, and then again S2 is stable for the inputs 0 1 or 1 1. Okay, so this is let us say the transition graph for asynchronous machine. Now okay, so now let us consider some so these are just the symbolic states. Now let us consider some encoding. So over here we have considered certain encodings. So here S0 is coded as 00, S1 is coded as 01, S3 is coded as 11, and S2 is coded as 11, and S3 is coded as 10. So let us just look at some transition. Okay. So we'll just look at the situation here. So we start examining with S2. So here for 0 1 and 1 on it is stable anyway, and here and for the inputs, uh, for the inputs, uh, 0 0 or 1 0 as shown over here, it makes a transition to this state. All right, so now if you look at this, there is only a single bit change. So this is encoded as 1 1 and this is encoded as 1 0. So there is only a single bit change. So there is no problem. So let us look at some more transitions. Let us look at S3. So S3 on getting 1 1 makes a transition to S2, which is this. So no problem, because this also involves a single bit change. And on getting 0 1 makes a transition to S0. So there also you don't have a problem, because there you have a single bit change. All right. Now let us look at the situation at S0. So here, as you can see, on getting 0 0, so let us see, on getting 0 0, so if you get 0 0 as the input, then you make a transition to S3, which is fine, because again you have a single bit change. Now let us carry on further. Let us see what happens in S1. So in S1, on getting 0 0, you have a transition to S3. Okay. So now you see what is happening. You have so if you on 0 0, you make a transition to S3. Now you got 2 bit changes, because this is encoded as 0 1 and this is encoded as 1 0. So what we have seen is that in practice, these bit changes will not occur exactly at the same time. So suppose your change, so here it is 0 1, so 0 1 will not change to 1 0, so the 2 bit changes will not happen exactly at the same time, let us say. So what can happen? Say 0 1 can first become 0 0, so that is, so what is encoded as 0 0? So basically on this input 0 0, you want it to change to 1 0, but your the physical realization is such that it doesn't change to 1 0 directly. Instead it changes from 0 1 to say 0 0 first. All right. Now when it the moment it is 0 0, so on the input 0 0, it makes a transition to S3. So I think it makes a transition to S0. Thereafter, as on 0 0, it changes to S3 with only 1 bit change. So it ultimately comes to S3. Okay. So you wanted to come to S3 directly, but as it happens that this 0 1 doesn't change to 1 0 directly, suppose it changes to 0 0. Now your switching function will because now the present state has become 0 0, so and your input is 0 0, so on 0 0 it still makes the transition to S3. So what you find is that this transition, so we have considered only one change, So anyway, so this transition, instead of happening directly, it comes here and then it comes here. But that's not the only possibility. It can also change to, you know, it can also change to 1 1 and then change to 1 0. All right. So let us see what happens if it changes to 1 1. So if it changes to 1 1, so then what happens is that it uh, 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 sorry, on input, on input 1 second. So say if you first make a transition to 1 1, if you first, yeah, on input 0 0, so here, so you really don't know, any one of these two can happen, because you don't know which one is going to switch faster. uh, so in this case we considered the possibility when it changes to, so this 1 becomes 0 faster, and then this 0 becomes a 1. But if it happens the other way around, if this 0 changes to 1 faster before this 1 changes to 0, so you get 1 1. All right. And then your input is 0 0. So as you find that in this case it's still okay, because on input 0 0 you still come to S3. All right. So in this case it it's still okay. I mean, so this transition, which should have happened this way, it of course, if the two bits change exactly at the same time, then you can still have this transition. But as we have seen, if the bits change at different times, you still, I mean, for this case, you change to S0, and from S0 you change to S3, and here you change to S2, and from S2 you change to S3. All right. Now let us consider what happens on 1 1. So on 1 1 also you are supposed to come here. All right. So again, you could you know you could so this one could first uh, uh, you know uh, on 1 1. So again the transition could happen in the same way. So from 0 1, suppose you come here, and on 1 1, what happens? uh, so let us just see what is happening on 1 1. Yeah. So if yeah, then if then transition is to S2. Okay, we're just looking at this one first. Okay, so if 0 1 changes to 1 1, okay, let us just look at this first. Then transition is to S2, and okay, so now you see, uh, yeah, yeah. So now look at this situation. Here you are supposed to come. You are supposed to come from S1 to. You are supposed to come. One second. Okay, so I think this is a different file. Sorry. This is a different file. Let me just just a second. Okay, so let us just see what's happening over here. Yeah. So here, so what he wanted was that the transition. So on 0, 1, you wanted this transition to happen from here to here. Sorry, you wanted this transition to happen from here to here, but what is happening is because of this, it is instead so from 0, 1, it is changing to say 1, 1, and then it should, you want it to change to 1, 0, right? But what is happening is, so this is on now on 1, 1, okay, on 1, 1. So on 1, 1, let us say it comes here. So as shown over here, it's coming here. But over here you have a problem, because on 1, 1, this one is, as you can see, it comes back here. So this is on 1, 1. So instead of, it is not coming here, it is getting trapped. Okay, it is getting trapped. So what you find is that this state assignment is problematic, because this transition, this particular transition, so let us just do it this way. So this particular transition on 1, 1, this one is problematic. It is problematic because it doesn't, it may not happen. It may not happen because, as you can see, it is coming here and getting stuck over here. All right. So this is a problem. So what you see is that the state assignment, an arbitrary state assignment may not work. You don't have this problem for synchronous circuits, because for synchronous circuits, what happens is that all the new state variables, those wait, and all of those are simultaneously transferred to the the flip-flops on the clock edge. Okay, so you don't have this problem for synchronous circuits, but for asynchronous circuits, you find that you can have this problem. So let us just so that's the problem. All right. So this is the thing. We'll not move to S3. All right. Now let us look at the others. I think. Okay. So now let us see. So from 01 to 00. So of course it could come here, as we saw before. It could come here, and here what happens on 1 1. Okay. So let us just see if then the transition is to S0, which on 1 1 has a transition to S2. Okay. So now on 1 1 this has a transition to S2. Okay. This one has a transition to S2. But with so 1 second. So if you have 0 1 2, then the transition is to S0, which on 1 1 has a transition to S2. So here you have, oh sorry, it has a transition to S2. Okay, so here again you have a problem. So here you want this transition. So here again on 1 1 the transition is not directly to S3, it is to S2. So there is a basic problem here. But again, this transition also involves 2-bit changes. So if you investigate further, so what is happening is, as it tries to move to S2, if you have you have a single bit change, so it might come back here, and then so it might come back here. Okay, and this on 1 1. Okay, and this on 1 1. This on 1 1 could move over here. Okay, so again it doesn't come here, instead it is going somewhere else. Or if you don't if it doesn't change to 0 1, it could change to 1 0. So in that case, let us say in that case it can come here. So what you find is that this the transition to 1 1 is problematic. If it changes to this directly, it gets caught over here. If it changes to this, there is a possibility of it coming here, but it could get caught. It could make a transition to this, and again on 1 1 the same thing could happen. So it could get caught in the cycle. Okay. It could get caught in the cycle, because as you saw, as you saw on 1 1, it could either come here or it could come here. So there is a possibility of getting caught in the cycle. So it is again problematic. All right. Now you have another situation. So as you can see, I think we need not go through all of these. So the point is that when you have transitions which involve multiple bit changes, you could have problems. So you'll have to be very careful about how the the state assignment and how the transitions can be handled. So this was just to illustrate the problem. So now let us look at the solution. So let us just see what is happening. So we would like, what you have seen is that we would like the encoding, we would like the transitions to happen in such a way that only one bit change is involved. Okay, only one bit change is involved. So what we have done is, in this case, we have just tried to embed this into into so this one uh, is you can say uh, you can say uh, well, we have got four states here. Okay, we have got four states here. So let me just draw something. Let me just draw a hypercube here. Let me just draw a hypercube. Okay, so I'm drawing, several hypercubes. So this is a single bit hypercube. So you have 0 and you have 1, and then this is a single bit change. Suppose you have two bits. So 2 bits, you have 4 possibilities, right? Sorry. So 0 0 0 1 1 0 1 1. Okay. You have 4 possibilities, and these are transitions that involve single bit change. Okay. So this is a hypercube of 2 bits. Now we can also have a hypercube of 3 bits. So let me just draw it on this itself. So we can have a hypercube of 3 bits. So let us say that this is the 0 plane, and this is the 1 plane, and here again we put 0 0 1 0 1 1. Just a minute, please. Okay, so sorry. Hold on. Last two questions. Sorry. So this is so here again, as you can see, this is actually just a copy of the earlier hypercube, and this is just a copy of the earlier hypercube. And here also you find that there is only a single bit change. Okay, there is also a single bit change here. So this hypercube is a nice structure. Okay, this is a nice structure. Why is it a nice structure? Because here what you can see is that the the transitions between these state encodings involve only a single bit change. So one strategy that we could adopt is, can we, if we could just embed this transition graph onto this hypercube, then our problem would be solved. Okay, so that is what I'll just illustrate now. That is essentially what we're going to do. So you look at this. So what is evident here? What is evident here is that this is not a proper embedding onto a hypercube. So you have transitions which involve multiple bit changes. For example, from this to this, you have got multiple bit changes. So now what we have done is we have just we have used 3 bits. Okay, we have used 3 bits. All right, and now what we are doing is we are embedding this onto a hypercube. Okay, we are embedding this onto a hypercube. So let me just, yeah. So if you look at this, so this is these are the states. So your original states are A, B, C, and D. So those states are here, A, B, C, and D. Now you have a transition from A to D. Okay, so as you can see, from A to D, this transition, what you are doing is you are routing this transition from A to D via E. Okay, you are routing this transition via E. So what you are doing is, so these are extra states. Okay, so these are extra states. So what you want to do is you want to have the, so the transition from A to D, you want to have, so this edge is going via this node. Okay, so here on 1 0 and 1 1 you have the transition to D as before. So what is happening is so from A to D on 1 0 and 1 1 you have a transition to E, and from E on 1 0 or 1 1 you have a transition to D. Now let us look at the transition from C to A. So from 0 0, so here it is 0 1 1. From 0 1 1 to 0 0 0, again you have got 2 bit changes. So if you come via E, so on 0 0 you are coming to E. So you define the next state of E as A on 0 0. So you ensure that the transition from C to A will happen on this path, can happen on this path. Okay, so on 0 0 it goes to E, and from E it comes to A. So similarly you find that say from D, so from D if you want to go to C, so here on 0 1 you want to go to C. Okay, so on 0 1 you want to go to C. So you have transition to the intermediate step F here, and from F you define a transition to C on 0 1, and from D you also have a transition to B. Now here you have got multiple bit changes. So here the transition to B is a bit more complicated. So on transition to B is on 0 0. So what you're doing is from B, so from D to come to B, you can't you have to go through additional states. So here you're going to F, and from F you define a transition on 0 0 to go to G, which is 101, and then from G you can come to B. So essentially what you have done is you have embedded this this graph, this transition graph, along with the edges onto this hypercube, and of course in doing so you had to you had to recruit some new you had to recruit some new nodes which allowed you to make these the transition safely. So what you found is that in the earlier examples, because of the state encoding, certain transitions were going haywire. They were not happening correctly. But with this kind of embedding onto a hypercube, now you can be sure that all the transitions are happening as you want them to happen. Of course, some of those transitions are not direct. So these transitions are direct as desired. These transitions are direct, but the remaining transitions are going through these intermediate states, and the the transitions are defined according to the embedding. All right. So that is how we can do the state assignment so that the transitions can be done safely. Okay. So that is how we can do the safe state assignment for an asynchronous machine. All right. So that is uh, the so for this we are not immediately giving an algorithm, uh, but we are just outlining how this can be done. All right. So is that okay? Do you have any questions regarding what we have, what has been demonstrated now? Yeah. Aryan, Aryan Singh, do you have any